70,000 gallons departed the North African depot on a Tuesday morning. By Friday, 30,000 gallons reached the front line. The other 40,000 vanished, evaporated into the Saharan sand grain by grain, seam by seam, leak by leak. The quartermaster filed his report with steady hands. Acceptable delivery ratio under field conditions. This wasn't sabotage. This wasn't enemy action. This was Allied engineering, and it was bleeding the war dry. September 1942. Richard M. Daniel steps off a transport plane in Cairo, his chemical engineering degree from MIT feeling suddenly small against the scale of the desert stretching before him. The War Department cable in his briefcase uses the word investigate, but the temperature rising through his field jacket tells him he's here to witness a crime scene where the murder weapon is invisible. His first briefing lasts 11 minutes. British quartermaster units are hemorrhaging fuel at rates between 30 to 40% from port to front line. War correspondent Alan Moorhead's dispatch sits on the table, underlined in red. 2 hours of bumping over desert rocks usually produced a suspicious smell. The great bulk of the British Army was forced to stick to the old flimsy 4-gallon container. General Auchinleck's estimate: 30% of all fuel never reaches its destination. Daniel watches a supply sergeant demonstrate the problem. The man hoists a British flimsy, a thin tin rectangle that sounds hollow even when full. He sets it down with exaggerated care. The corner buckles. He tilts it. Fuel seeps from a seam that wasn't leaking 5 seconds ago. The sergeant doesn't speak. He just looks at Daniel with the exhausted patience of a man who has explained this 10,000 times to 10,000 superior officers who can't fix it. These flimsies are packed in wooden crates, sometimes plywood, sometimes cardboard. Each layer of protection and admission that the container itself is essentially a single-use coffin for gasoline. Soldiers call them other names too, none printable in official reports. The American containers aren't salvation. They're just a different flavor of failure. 5-gallon rectangular cans with screw caps and cork gaskets. World War I technology trying to fight a World War II mechanized war. The caps require wrenches. The pouring requires funnels. The lifting requires 2 men and a prayer that the gasket holds. Daniel spends his first week watching fuel seep into sand. It pools in tire tracks. It stains the wooden beds of supply trucks. It turns the air shimmering and dangerous around every depot. He does the math in his head, then on paper, then in a cable to Washington. 40% fuel losses. He would admit 45 years later in his 1987 article, The Little Can That Could, that this number was less calculation than provocation, a guess calibrated to trigger alarm. But whether it was 40%, Auchinleck's 30%, or that documented 57% case, the mathematics of catastrophe remained unchanged. Then Daniel sees the German can, a captured supply dump near the front. Allied soldiers are already fighting over the contents, but not for ammunition or rations. They're grabbing green steel containers, tucking them under arms, hoarding them like gold bars. These containers look new. After months in the desert, after being dropped, stacked, baked at 120 degrees Fahrenheit, frozen at night, tossed from truck beds. They look like they just came off a factory line. The men call them jerry cans, British slang turning the enemy into a nickname for the one piece of German equipment every Allied soldier desperately wants to steal. Daniel picks one up. It's heavier than it should be, not from fuel, but from engineering. 3 handles, 2 short grips on the sides for one-handed carrying, 1 long handle across the top for 2-handed hauling or passing in a supply chain. The surface isn't smooth. It has an X-shaped indentation pressed into both faces, ribs that look decorative until you realize they're expansion chambers for the fuel inside. He runs his finger along the seam, recessed, welded, invisible unless you're looking for it. On the Wehrmacht Einheits canister, Armed Forces Unit canister, was born in 1937 at Müller Engineering Works in Schwelm, Westphalia. German engineer Vinzenz Grünvogel spent 3 years perfecting it. After a competitive tender in 1935-36, a test series of 5,000 cans went to troops in 1936. The German Army officially adopted it on July 8, 1937 via Order AHM number 324, 3 years of testing before the first shot of the war was fired. By 1939, the German military had stockpiled thousands. Motorized troops received jerry cans alongside rubber hoses for siphoning fuel from any source, a tactical doctrine built around a container. When the Wehrmacht tore through Poland, their logistics flowed like water because their containers didn't leak like sieves. 20 liters, approximately 5.3 US gallons. In 2 stamped sheets of steel welded together with that recessed X seam, interior dip-coated against corrosion, a self-venting cap that released pressure without spilling, a pouring spout that could empty the can in 12 seconds without a funnel. Every detail had a reason. Every curve had a function. And Daniel, standing in the Egyptian heat with diesel fumes in his nose and failure pooling at his feet, understands that the Allies are losing a war of engineering before they ever fire a shot. But here's what Daniel doesn't know yet. An American engineer named Paul Pleiss carried the solution into Washington 3 years earlier. In 1940, Pleiss traveled from Berlin to the War Department with a jerry can under his arm and specifications in his briefcase. He demonstrated it, explained the welded seam, showed them German precision, the U.S. The military looked at the sample, consulted their manufacturing timelines, and declined. Institutional inertia trumped German perfection. When America finally decided to copy the jerry can in 1942, engineers at Camp Holabird in Maryland studied the design. They saw the 3 handles, copied those. They saw the X-shaped indentation, copied that. They saw the overall shape and capacity, copied everything visible. But the welded seam was recessed, hidden, invisible to casual inspection. American engineers made an improvement. Replaced the expensive, time-consuming welded seam with a rolled crimp seam, faster to manufacture, cheaper to produce. Looked almost identical from the outside. On paper, it was brilliant cost-cutting. In the desert, it was a death sentence. The 120 degrees Fahrenheit heat made steel expand. And the rolled seams, just crimped metal folded over itself, flexed under pressure. Fuel found the microscopic gaps. What started as seepage became hemorrhaging. Supply trucks became rolling fire hazards. Soldiers abandoned millions of American-made cans across North Africa and Europe, still hoarding every captured German original they could find. By August 1944, General Patton's Third Army was tearing across France at lightning speed, until the invisible flaw caught up. The fuel existed in the rear depots. The trucks existed to transport it, but there weren't enough working containers to bridge the gap. The entire Allied advance halted at Metz. Not stopped by German bullets, not halted by enemy strategy, stopped by a crimped metal joint that saved 3 cents per can. Daniel's boots hit Egyptian sand on September 14, 1942, and within 3 hours he understood why Washington had sent him halfway around the world with orders marked urgent. The fuel depot at Alexandria sprawled across 12 acres of cracked earth, row after row of containers stacked like a metallic graveyard. But the smell hit him before the sight. Gasoline fumes so thick they distorted the air, creating shimmering walls of vapor in the morning heat. The depot commander, a British major named Thornton, with sun-scorched skin and permanently narrowed eyes, walked Daniel through the mathematics of disaster. "We received 180,000 gallons from the tankers last week," Thornton said, his voice carrying the flat affect of a man reciting numbers he's long stopped believing. "By the time it reaches the forward units, I will be lucky if 110,000 makes it." Daniel did the calculation in his head. 39% loss. "Where does it go?" he asked, though the answer was already pooling beneath his feet, dark stains spreading through the sand like bloodstains on a battlefield. Thornton gestured toward a supply truck being loaded 50 yards away. 2 soldiers were stacking containers in the bed, moving with the exaggerated care of men handling explosives. Even from this distance, Daniel could see the wet streaks running down the sides of the cans, the sand beneath the truck turning dark and shiny. "There," Thornton said. "And there. And there." He pointed to 3 more trucks, each surrounded by the same telltale darkening of the desert floor. "It seeps during loading. It leaks during transport. When the trucks hit rocks, and they will hit rocks, mister." "Daniel, because this is the Sahara, not Pennsylvania, the seams split and we lose gallons at a time. The men have learned to drive with their windows open because the fumes build up in the cab. We've had 2 trucks catch fire this month from gasoline vapor and a single spark." Daniel pulled out his notebook, but his pencil hovered over blank paper. What could he write that would make Washington understand? That the British Empire was fighting a mechanized war with containers that belonged in a museum? "Show me the worst ones," he said. Thornton led him to a section of the depot the soldiers had started calling the graveyard. Here sat the containers deemed too damaged for even one more journey. Hundreds of them, maybe thousands, stacked in rusting pyramids. Daniel picked up the nearest one. The metal was so thin he could feel it flex in his hands. The kind of gauge you'd use for a biscuit tin, not a fuel container carrying the lifeblood of an army. The British called them flimsies, and the nickname was generous. Each one held 4 imperial gallons and weighed almost nothing empty because there was almost nothing to them. Just stamped tin with soldered seams that failed under any stress more severe than a strong wind. The design dated back decades, created for a world where fuel was transported by rail to stationary depots, then dispensed by patient men with funnels and time to spare. Daniel watched a supply sergeant demonstrate the standard procedure. The man set a flimsy on the ground, unscrewed the cap, which required a wrench because the threads were already stripped, inserted a funnel, and then began to pour into a vehicle's tank. Gasoline immediately began leaking from the seam where the handle attached. The sergeant didn't even look down. He just shifted his feet to avoid standing in the pooling fuel. "They come packed in wooden crates," the sergeant explained, his accent placing him somewhere in Lancashire. 2 cans per crate. The crates add weight, add cost, add loading time, but without them the cans crush each other when stacked. We switched to plywood crates to save weight, then cardboard. You can imagine how cardboard holds up in desert humidity. He gestured at a pile of disintegrated boxes, fuel-stained and collapsed. "Most of these cans make one trip. One. We're running a war on disposable containers." Daniel spent the afternoon documenting failures. Seams that split when the temperature spiked above 110 degrees Fahrenheit. Handles that tore free when fully loaded. Caps that stripped or cross-threaded, turning a sealed container into an open bucket. By evening, his notebook was full and his estimate was forming, not from rigorous calculation, but from the visceral certainty that comes from watching an empire bleed out 1 gallon at a time. That night, he drafted his cable to Washington. Estimate 40% fuel losses between port and front line. Crisis worse than initial reports suggested. Immediate action required. 45 years later, he would admit this number was calibrated more for psychological impact than scientific precision. But standing in that depot, watching gasoline evaporate into desert air while men died for lack of fuel at the front, precision felt less important than alarm. The next morning, a young lieutenant found Daniel at breakfast. "Sir, you should see what came in last night. Captured German supply dump about 40 miles west. The men are going crazy over something." Daniel hitched a ride on a supply truck, and what he found looked less like a military salvage operation and more like a gold rush. Allied soldiers were swarming over captured German containers, grabbing them, arguing over them, treating them with a reverence usually reserved for ammunition or water. These weren't flimsies. These weren't American rectangles with cork gaskets. These were something else entirely. Daniel pushed through the crowd and picked up one of the containers. The first thing he noticed was the weight, substantial, engineered, the heft of something built to last. The second thing was the color, a deep olive drab green that seemed to absorb the desert light rather than reflect it. And the third thing was the handles, 3 of them, arranged in a configuration that seemed obvious once you saw it, but revolutionary in its simplicity. He ran his hands over the surface. The container wasn't smooth. It featured an X-shaped indentation pressed into both the front and back faces, creating 4 raised quadrants. The design looked decorative until you thought about thermal expansion, about how fuel heats and cools, about how metal needs room to flex without the seams tearing apart. A corporal standing nearby noticed Daniel's examination. "Jerry cans, sir. That's what the boys are calling them. Jerry for Germans. Cans for, well..." He hefted one appreciatively. "These things are worth more than captured weapons. I've seen men trade chocolates, cigarettes, even ammunition for a good jerry can. This one's been in the desert for 6 months according to the markings, and look at it, looks factory fresh." Daniel turned the container over in his hands, studying the seam. It took him a moment to even find it, a recessed weld running down the center, barely visible, engineered to sit below the surface where stress couldn't reach it. The cap was self-venting, releasing pressure without spilling. The pouring spout had a cam lever mechanism that could empty the entire can in seconds without requiring a funnel. 20 liters, the corporal said. About 5¼ gallons. One man can carry 2 full ones or 4 empties using the side handles. You can pass them in a chain during loading. The Germans thought of everything. Daniel had seen enough engineering in his career to recognize genius when he held it. And this wasn't just a container, it was a complete system, a philosophy of logistics made manifest in stamped steel. Every curve had a purpose, every feature solved a problem. The X indentations allowed for expansion. The 3 handles enabled multiple carrying configurations. The recessed seam eliminated the weak point that destroyed every Allied container. Somewhere in Germany, an engineer had sat down and designed this. Not quickly, not cheaply, but perfectly. That engineer was Vinzenz Grunvogel, though Daniel wouldn't learn the name for several more months. In 1937, Grunvogel worked at Müller Engineering Works in Schwelm, a small industrial city in Westphalia where precision manufacturing was a matter of regional pride. The German military had issued a tender in 1935 for a new standardized fuel container. The Wehrmacht was modernizing, mechanizing, preparing for a kind of warfare that required fuel to flow as reliably as ammunition. Grunvogel approached the problem like a mathematician approaches a proof, by identifying every variable, every stress point, every failure mode, and then designing each out of existence. He studied how soldiers carried equipment. He calculated thermal expansion coefficients. He tested seam constructions under temperature extremes from -20 to +50 Celsius. He refined the handle placement through ergonomic trials, watching men load and unload containers until the optimal configuration revealed itself. The test series of 5,000 cans went to troops in 1936. For a full year, German soldiers used them, abused them, reported back on every flaw and weakness. Grunvogel incorporated the feedback, adjusted the specifications, and perfected the details. On July 8, 1937, the German Army issued Order AHM No. 324, officially adopting the Einheits canister, the universal container. 3 years before the war began, Germany had solved fuel logistics. By 1939, they had stockpiled thousands of these containers. When Wehrmacht motorized units rolled into Poland, they carried jerry cans and rubber siphon hoses as standard equipment, a doctrine that turned every abandoned vehicle and depot into a potential fuel source. The containers didn't leak, they didn't buckle, they didn't fail. The Allies had noticed. Of course they had noticed. In 1940, an American engineer named Paul Pleiss stood in a Berlin warehouse staring at the same green containers Daniel would discover 2 years later in the Egyptian desert. Pleiss worked for a firm with German business connections, and someone in the U.S. military had enough foresight to send him hunting for any technology worth copying before the shooting started in earnest. Pleiss didn't just observe, he obtained. He secured a sample jerry can and a complete set of manufacturing specifications. He understood immediately what he was looking at, a solution to a problem the American military didn't yet know it had, but would. The journey from Berlin to Washington took 3 weeks. Pleiss carried the jerry can through customs, onto trains, into War Department offices. He demonstrated the 3-handle system. He explained the recessed welded seam and why it mattered. He showed them German engineering at its finest, a masterpiece of practical design that could be copied, adopted, mass-produced. The officers were polite. They took notes. And they examined the container with the casual interest of men reviewing something that might be useful someday, but not today. Not with 1,000 other priorities and a peacetime budget and manufacturing pipelines already established for existing designs. Institutional inertia has its own gravity, stronger than logic, heavier than evidence. The U.S. military thanked Pleiss for his initiative and sent him home. The jerry can, the sample, the specifications, the solution to a crisis that hadn't yet emerged, went into a file somewhere in Washington. 2 years later, Daniel stood in the Egyptian desert holding that same design, now scavenged from enemy supply dumps because the Allies were hemorrhaging fuel through containers that belonged in the last war. And somewhere in a Washington file cabinet, Pleiss's specifications gathered dust while soldiers died for lack of gasoline that had leaked into sand. By early 1943, Daniel's reports had finally penetrated the bureaucratic fog in Washington. The War Department issued orders: copy the German design, manufacture it domestically, flood the supply chain with containers that actually worked. The assignment went to the Quartermaster Corps facility at Camp Holabird in Maryland, where engineers gathered around captured jerry cans like surgeons studying a particularly elegant procedure. They measured everything: the 20-liter capacity, the overall dimensions, the 3-handle configuration, the X-shaped indentations pressed into both faces. They documented the cam lever cap, the self-venting mechanism, the pouring spout geometry. They created technical drawings, established tolerances, calculated material requirements. But the recessed welded seam presented a problem. Welding required skilled labor, specialized equipment, quality control that slowed production. Each seam needed to be precisely aligned, the 2 stamped sheets joined with a bead of molten metal, then ground down to sit below the surface. It was time-consuming. It was expensive. And America was now fully committed to a 2-ocean war that demanded containers by the millions, not thousands. The Camp Holabird engineers proposed an improvement: replace the welded seam with a rolled crimp seam. The concept was simple: fold the edges of the 2 sheets together, crimp them tight, create a mechanical seal that looked nearly identical to the welded version but could be formed in a fraction of the time. No welding required, no specialized labor, just stamp, fold, crimp, move to the next one. On paper, it was brilliant cost engineering. The rolled seam would sit in roughly the same recessed channel as the welded seam. The overall appearance would be identical. The manufacturing time would drop by 60%. The unit cost would decrease by 43 cents. Multiply that by millions of cans, and the savings looked like strategic genius. No one asked why the Germans had chosen welding. No one questioned whether Grinvogel had tested crimped seams during his 3 years of development and rejected them for a reason. The assumption was obvious: German over-engineering, Teutonic obsession with perfection when good enough would suffice. America would take the German design and make it practical, efficient, ready for mass production. The first American jerry cans rolled off production lines in spring 1943. And they looked right. The dull gray-green paint, the USA stenciled on the side, the 3 handles, the X indentations, everything visible matched the German original. Supply officers requisitioned them by the tens of thousands. Soldiers loaded them onto trucks with relief, grateful to finally have something better than flimsies. For the first month, they worked perfectly. The second month, reports started filtering back. Seepage. Not catastrophic splitting like the flimsies, but persistent weeping from the seams, especially in hot weather. Supply sergeants noticed dark streaks running down the sides of cans that had been fine yesterday. Quartermasters reported fuel levels dropping during transport, even when caps remained sealed. By month 3, the pattern was undeniable. The American jerry cans were failing. And they were failing in a way that traced directly to the invisible modification no one had questioned. The desert provided the verdict with brutal efficiency. When temperatures spiked above 115 degrees Fahrenheit, the fuel inside expanded. The steel expanded. The pressure built inside the can exactly as Grunvogel had calculated it would back in 1937, which was why he designed expansion chambers into the X indentations. But expansion creates stress, and stress finds the weakest point in any structure. In the German design, that weakest point didn't exist. The welded seam was a continuous bond of fused metal, as strong as the sheets themselves. In the American design, that weakest point was everywhere along the crimped seam. The folded edges, held together by mechanical pressure rather than molecular fusion, flexed microscopically. Fuel found the gaps. Thus, what started as beads of seepage became steady leaking. Cans that seemed fine in the morning were half empty by afternoon. Soldiers learned to stack American cans with the seams facing up to minimize losses. They learned to check seams daily, abandoning cans at the first sign of failure. They learned to hoard every captured German can they found, because those never leaked, never failed, never turned a supply truck into a rolling fire hazard from gasoline vapor building up in the cargo bed. The mathematics of disaster compounded quickly. If a flimsy lost fuel through catastrophic splitting, you knew it immediately and could transfer the remaining fuel to another container. If an American jerry can wept fuel through a crimped seam, you didn't notice until the can was light. The fuel already evaporated into desert air. The waste invisible until inventory time revealed the shortfall. Daniel, still in North Africa tracking logistics, watched the crisis evolve from flimsies to something more insidious. The British containers failed spectacularly and obviously. The American containers failed quietly, persistently, in a way that made the losses harder to track, but no less devastating. By August 1944, the crisis reached its crescendo not in the desert, but in the fields of France. General George Patton's Third Army had broken out of Normandy and was tearing across the French countryside at a pace that stunned both the Germans and Allied high command. Patton's tanks covered 50 miles some days, then 60, then 70, a mechanized blitzkrieg that consumed fuel at rates the supply chain had never anticipated. The fuel existed. Depots in the rear had millions of gallons stockpiled. The trucks existed to transport it forward, but the containers, the critical link between fuel at rest and fuel in motion, were failing faster than they could be replaced. Patton's units began reporting shortages in late August. Not because tankers weren't arriving from Britain, not because depots were empty, but because there weren't enough functioning containers to move fuel from depot to front line. The American jerry cans were leaking, being abandoned, failing at rates of 20 to 30% during a single journey. Soldiers were still hoarding captured German cans, but there weren't enough of them. The flimsies had been mostly phased out, but their replacements were proving almost as unreliable. On September 2, 1944, Patton's advance halted at Metz. The German border was within reach, and the Wehrmacht was reeling, disorganized, vulnerable. But the Third Army couldn't move because the tanks were dry and the fuel was 200 miles back, sitting in depots, waiting for containers that could survive the journey forward. The war, a conflict of tactics, strategy, mechanized might, had been stopped by a crimped metal seam. The British, watching this catastrophe unfold with the weary recognition of people who had suffered through flimsies, made a different decision. Their engineers obtained German jerry cans and began reverse engineering them with one critical difference in approach. They assumed every detail was intentional. The recessed seam, welded, exactly as Grünvogel designed it. The three handles, positioned at the precise angles of the German original. The X indentations, stamped to the exact depth specifications. The British didn't try to improve, streamline, or economize. They copied with the humility of students learning from a master. British factories began producing faithful jerry can reproductions in late 1943. By mid-1944, they were manufacturing them by the hundreds of thousands. British supply units stopped losing fuel to seepage. Their containers survived the journey from depot to front line intact. When Patton's fuel crisis emerged, British manufactured jerry cans began supplementing American supplies, and the difference was immediately obvious. The British versions worked, consistently, reliably, exactly as the German originals had worked. The Americans eventually corrected course. By late 1944, new manufacturing specifications went out requiring welded seams. Factories retooled. And the cost savings from crimped seams had proven to be the most expensive economy in the history of military logistics, measured not just in wasted fuel, but in halted advances, delayed victories, prolonged campaigns. The war ended in May 1945. Germany surrendered. The Wehrmacht's mechanized forces were destroyed, scattered, their fuel logistics irrelevant in defeat. But Grünvogel's container, designed in 1937, perfected through 3 years of testing, built on the principle that every detail mattered, survived its creator's regime. The jerry can became the NATO standard, not the American version with its cost-saving modifications, not the British flimsy or the obsolete American rectangular cans. The German design, faithfully reproduced with welded seams and 3 handles and X indentations, became the global specification for portable fuel containers. 90 years later, you can walk into military depots from Belgium to South Korea and find descendants of Grünvogel's 1937 design. The specifications have barely changed. The fundamental engineering remains identical. Modern materials have replaced steel in some versions, plastic polymers, composite materials, but the shape, the handles, the expansion chambers, the principles remain. The American military learned what Daniel had tried to tell them in 1942, what Pleiss had tried to show them in 1940, what every captured German supply dump had been screaming since the war began. Details determine outcomes. The difference between a welded seam and a crimped seam seemed invisible, seemed trivial. It seemed like the kind of over-engineering that practical American ingenuity could improve upon. That invisible difference stopped an army. In 1987, Richard M. Daniel published The Little Can That Could, and admitted his 40% loss estimate had been more alarm than analysis. But he also noted that the real losses, whether 30%, 40%, or that documented 57%, mattered less than the lesson. The Allies had fought a war with containers designed for peacetime, then tried to copy genius while cutting corners, and the desert, the heat, and the relentless physics of thermal expansion had provided the final grade. The jerry can sits in museums now, displayed next to tanks and rifles and field radios. But unlike those weapons of destruction, the jerry can was a tool of logistics, of the unglamorous mathematics that determines whether armies move or stall, and whether campaigns succeed or collapse. It's a monument to the idea that excellence has no shortcuts, that invisible details carry visible consequences, that the enemy's design might be perfect for reasons you can't see until you've already failed. Grunvogel died in 1970, his name largely unknown outside engineering circles. But his creation outlived him, outlived the regime that commissioned it, outlived the war it was designed to fight. Every time a soldier fills a jerry can, every time fuel reaches the front line without leaking into sand, every time logistics flow smoothly enough that no one even notices, that's Grunvogel's legacy. That's what happens when someone designs something right the first time, when someone refuses to compromise on the details everyone else considers invisible. When someone understands that the difference between genius and disaster often comes down to 3 words: welded, not crimped. If stories like this help keep history alive, support the channel by liking the video and subscribe for more forgotten World War II stories. Turn on notifications so you don't miss the next one. Drop a comment, tell us where you're watching from.